So in previous lecture, we had discussed about various terms involved in the metallurgy, and we also understood that in order to extract pure metal from its minerals or the ore, there are three main steps required. The first step is what? Concentration. Second is what? Extraction. And the third is what? Refining. So we had discussed about concentration. Basically, student, concentration involved removal of earthy impurities, and these earthy impurities we had termed as what? Gangue. Since the gangue is of various types, so removal of these gangue particles required different methods, and we had discussed these methods like gravity separation, which were applied for all types of ore, froth flotation for sulphide ore, leaching for aluminium, silver and gold, and also we did magnetic separation. So all these methods which we are carrying out only to remove what? Gangue particles from the metal compounds. But even applying all these methods, student, we are not able to remove all type of the gangue particles. There are certain type of the gangue particle, some impurities which requires heating to remove. So after doing concentration, once the ore is obtained, which is consisting of less amount of gangue and more amount of metal compound, which we referred as what? Concentrated ore. So this concentrated ore is subjected to the next step, that is what? Extraction. So in this session we will talk more about what? Extraction. So basically we carry out extraction, student, to remove those type of the impurities where we are unable to remove impurities in the earlier step, that was what? Concentration. So basically for removal of impurities in the extraction part, we heat the concentrated ore. So in science, when we say extraction, the easy way to define extraction is this. We can say the process used to obtain metals in free state. If you see this part, what they are saying, the process used to obtain metals in the free state from a very important concentrated ore. So for extraction, since extraction is taken as the second step, and before this we were doing what? Concentration. So the ore which is obtained after concentration process, which is free from impurities, is referred as what? Concentrated ore. So if you'll see, the process used to obtain metals in the free state from concentrated ore is referred as what? Extraction. So when we deal with the second step of the metallurgy, that we referred as what? Extraction. So extraction is consisting of two steps, and in both the steps, if you will see, we are converting metal compound. Now this metal compound is present into the concentrated ore. So this metal compound is converted to what? Metal oxide. But we don't want metal oxide, student. We actually want free metal. So we have to remove this oxide part. So removal of oxygen will lead to the formation of free metals. So this process of conversion of metal oxide to free metal is referred as what? Reduction process. But reduction is the next step that we involve in the extraction. Before this, we convert this metal compound into metal oxide by a process of what? Oxidation. So first we carry out oxidation, and the second we carry out what? Reduction. Let's move to the first step. Since metal compound, in order to convert into the metal oxide, this metal compound is heated in presence of atmospheric air. Here the atmospheric air acts as what? Oxidizing agent. So this heating involves removal of volatile gangue, and it can be done by two methods. The metal compound present in the concentrated ore can be heated by using limited supply of air or absence of air, or it can be heated in presence of excess of air. So if you'll see, there is difference. This metal compound, in order to convert to metal oxide, we are heating this metal compound. One, we can heat in the limited supply of air, and it can be heated to excess of air. This totally depends upon the type of the metal compounds. So if the metal compound is converted to metal oxide by heating in the limited supply of air, then this process we refer as what? Calcination. Generally, we apply calcination for carbonate ore of the metal. And if the ore is heated in the excess of air, then this process is referred as what? Roasting. So calcination and roasting are the two major steps involved in the extraction, where we convert metal compounds to metal oxides. Got this? So calcination is basically carried out for carbonate ore, and roasting is carried out for what? Sulphide ore. After this, if you will see, this both process involve common chemical reaction, which is what? Oxidation. And during this oxidation, what happens? The metal compounds gets converted to metal oxide, and it's all volatile impurities, and the moisture is given out. Once the metal oxide, we want to convert to the free metal, we have to carry out the process of reduction. But the method of reduction, it depends upon the reactivity of the metal. So there are various methods of reduction that we apply. One which is referred as what? Chemical reduction, and one which is referred as electrolytic reduction. See, chemical reduction is carried out in the aqueous solution by using some chemical reagent. It is also referred as hydrometallurgy. In the second case, it is referred as electrolytic reduction, student. So electrolytic reduction actually involves the principle of electrolysis, and chemical reduction can also be carried out by heating the compound. If it involves aqueous solution treatment, that is called hydrometallurgy, and if it involves heating, that is called as what? Pyrometallurgy. In electrolytic reduction, I told you it involves the process of what? Electrolysis, and here if you will see, this process is called as what? Electrometallurgy. So reduction, there are three different methods. One is hydrometallurgy, pyrometallurgy, and electrometallurgy. In this, if you will see, student, the major step first is what? We oxidize metal compound to metal oxide by a process of calcination and roasting. Metal compound which is present in the concentrated ore is consisting of volatile impurities. These volatile impurities cannot be removed by normal concentration method, so we need to heat these metal compounds. So if we are heating this metal compound in the presence of atmospheric air, which acts as oxidizing agent, so it oxidizes metal compounds to metal oxide. So this is done by a process of calcination or roasting. So let us understand one by one what are these processes. Let us understand first calcination. So in science, when we talk about calcination, so first it is a process of extraction. And what are the things happening in this, student, if you'll see? It is the process of converting. It is very important. What type of the ore is taken under this process? So it is a process of converting an ore into its oxide by heating it strongly below its melting point. Now the question is that why we are heating below its melting point? Because it prevents burning of the metal compound. If you will increase the temperature, then it can burn the metal compound. So we have to prevent metal compound from the burning. That's why we keep temperature below its melting point. So calcination is the process of converting an ore into its oxide by heating it strongly below its melting point, either in absence of air or sometimes limited supply of air. You got this? See what type of the changes happens during heating or in calcination. So these are the following changes which takes place. If you'll see, the very first thing, if the concentrated ore is consisting of what? Moisture. Now this moisture can be because of the hygroscopic nature of the ore, means the ore absorbs moisture from the surrounding, or sometimes this moisture is associated if the ore is hydrated. So on heating this, the very first thing is what? This moisture is given out. It makes the ore, concentrated ore, to what? Dry. Second thing, if the water is removed from the hydrated ore, let's take example of this, student. If you will see this Al2O3.2H2, along with the Al2O3 we can find, student, there is dot 2H2. So this dot 2H2O is actually indicating what? Water of crystallization. If any compound is consisting of water of crystallization, then we say that compound is what? Hydrated. So here what they are talking about, water is removed from hydrated ore. So if you will heat this, so what will happen? This part will get removed and it will form a dry substance, anhydrous substance. This anhydrous substance Al2O3 we referred as what? Alumina, and this alumina we obtained from naturally obtained mineral from the aluminium, which is called as what? Bauxite. So bauxite can be converted to alumina by the process of calcination. So here the purpose of doing calcination is only to remove this moisture. Similarly, another reaction, if you will see, this is Fe2O3. Again, if it is heated, can you see it is consisting of some amount of the water molecule? So this is again hydrated. So if it is heated, this water will easily remove and you will get what? Anhydrous ore. This Fe2O3 hydrated part is referred as limonite, and when this limonite it is heated, it gives what? Ferric oxide. So in two examples, if you'll see, the calcination is helping driving out of the moisture, and the second, the water is removed from the hydrated ores. But there is another advantages of this calcination, student. Calcination is basically carried out for carbonates ore, because generally if you will see, if any carbonate compound is heated, so on thermal decomposition, carbonate compounds of the metal releases carbon dioxide and it forms the metal oxides. That's why they have written carbonate ore are converted into their respective oxide by loss of carbon dioxide. Let's take one example here, calcium carbonate. If you'll see, if the calcium carbonate is heated, so there is a loss of CO2 gas, and once the CO2 is removed, it is present, it gives the residual part. This residual part is consisting of oxides of metal, that is calcium oxide. Similarly, like calcium carbonate has converted to calcium oxide, it can also be applied for the other carbonate. For example, in the extraction of the zinc, if you will see, zinc carbonate, which is referred as calamine. Calamine, which is one of the ore of zinc, student, it is associated with what? Carbonate. So when this carbonate is heated, there is a loss of CO2 and this ZnCO3 gets converted to what? ZnO. Let's take another example, student. This is dolomite. In dolomite, if you will see, there are two metals, calcium and the magnesium, and both are associated with the carbonates. So on heating, what happens? This carbonate part, it evolves what? CO2 gas. So the residue which is obtained, it gives what? It's calcium oxide and the magnesium oxide. So in all the process, if you will check, then metal carbonates gets converted to what? Metal oxides. So this is also one of the advantage of what? Calcination. See, so after heating this, since all the impurities are removed, So the ore also becomes porous. When I'm saying porous, means it will be consisting of small holes. If the ore becomes porous, then the processing of that ore becomes very easy. For calcination and the roasting, in both the process extraction, the finally powdered form of the ore is heated in this furnace. Now, this furnace is referred as what? Reverberatory furnace. And if you look at the various parts of the reverberatory furnace, like charge hooper, second, it is consisting of small window-like structure, which we referred as what? Air vents. And it is consisting of, this inner lining is consisting of silicon carbide brick. Student, this is a special type of brick which is called as refractory brick. When you say refractory brick, means it is a chemical substance which can withstand with very high temperature. Since we are heating the powdered form of the ore for a long period of time, that's why purposely these bricks are made up to handle such temperature for long period of time. So this is the hooper, which is a conical flask-like structure. In this we just add powdered form of the ore, and from this powdered form of the ore, from here if you'll see, it just comes and it just collected at the bottom of this furnace. Now by using various fuel gases, which is acting as a source of heat, once it is heated, mostly the fuel gases that we are using is what? Producer gas, or it is water gas. So on heating this, as the temperature of this brick increases, it also increases the temperature of this powdered form of the ore, and we control the supply of air through this air vents. Once this entire metal compounds gets converted to metal oxide, then it is easily removed. Since in extraction we convert metal compound to metal oxide, and this can be achieved by two steps. One is what? Calcination, and one is what? Roasting. Just now we have done calcination, where we have converted metal compound to metal oxide by heating this metal compound into the limited supply of air. Now let us understand the next step, that is what? Roasting. So in case of roasting, in science generally it is applied for sulphide ore. If any metal is present in the form of sulphide or associated in the form of sulphide, then we do the process of what? Roasting. So in science, roasting, if you will see, it is a process in which ore are heated to high temperature but below their melting point. I had just explained in the calcination also. We are heating the ore, but at the same time we are preventing the ore from burning of the metal compound. So the temperature should not be above the melting point of the metal compound. That is the reason we are saying the ore are heated to a high temperature below their melting point in the presence of excess of air. Student, if you will compare with the calcination, calcination is carried out either in the limited supply of air or absence of air. But whenever we are doing what? Roasting, roasting is always carried out in presence of excess of air. These following changes can occur when the roasting is carried out for the concentrated ore. The very first thing, if the ore is consisting of the moisture, this moisture is removed. Along with this, if the metal compound is consisting of what? Volatile impurities. Now these volatile impurities can be sulphur, can be arsenic, or it can be phosphorus. These all non-metallic elements which are embedded with the metal compounds can act like volatile impurities. So during roasting, which is a process of oxidation, these non-metallic substances get oxidized and removed as volatile oxides. For example, if you will see, if the sulphur is present as the impurities, it immediately combines with the oxygen and it gets converted to what? Sulphur dioxide. So we have to remember this conversion. Sulphur impurity forms volatile oxide and gets converted to what? Sulphur dioxide. Similarly, if you will see arsenic, if the arsenic, sometimes arsenic is also present as impurities. So this arsenic also have tendency to get oxidized in the atmospheric air, and it forms its volatile oxide, that is arsenious oxides. So arsenic gets converted to As2O3, which we refer as arsenious oxide. If the phosphorus is present, which is again a non-metallic element and acting as impurities, so this phosphorus also get oxidized to form its corresponding oxides of what? P2O5. So like this way, if you will see, the volatile impurities which are associated with the metallic compound in the concentrated ore, on oxidation they get removed in the form of what? Gaseous oxide. Along with this, student, if you will see, what happened to the sulphide ore? Since the metal is present with what? Sulphur, it is associated with the sulphur. So while roasting, we are supplying excess of air, and that air acts as what? Oxidizing agent. So this oxidizing agent oxidizes the volatile impurities as well as the metal sulphide. So generally, the key point that we have to remember over here is metal sulphide gets converted to metal oxide. The principle of this, if you see, the sulphide ore is getting oxidized and it is forming what? Metallic oxide. Say for example, in case of zinc blend, student, zinc blend, which is also referred as what? Zinc sulphide, which is the chief ore of what? Zinc metal, where zinc is associated with the sulphur. So when the zinc sulphide is heated with the excess of air, like when the roasting is carried out, so this oxygen combines with the metal part also and the sulphur part also. So they both get oxidized, and the zinc sulphide forms oxide of zinc and the oxide of sulphur. This oxide of the zinc is the residual product, where the sulphur dioxide being gaseous product get evolved. So in this, if you will see, we are converting metal sulphide to metal oxide, and this is the part which is acting as the volatile impurities which get removed. Similarly, lead ore is also present in the form of what? Sulphur. Since it is present in the form of sulphur, so the best method to convert into its oxide is what? Roasting. So again, if this is heated in excess of air, so this oxygen gets combined with the metallic part, that is lead, and also it gets combined to what? Sulphur. So this both element forms their oxide, namely lead oxide and the sulphur dioxide. Now the sulphur dioxide gas is the gaseous product which get removed. It leaves a residue of what? Metal oxide. We can check some more examples also, student. This copper is also present in the form of sulphide. It's copper 1 sulphide. Now in this copper 1 sulphide, if you will see, again if it is heated in the excess of air, so this oxygen gets combined with the metallic part as well as what? Sulphur part. So it forms copper 1 oxide as the residue, and there is volatile impurities formed, which is sulphur dioxide. So in general, if you will see, whenever we are doing roasting, so always metal sulphide is taken under roasting, and this metal sulphide gets converted toward metal oxide. In case if it contains any volatile impurities, then this volatile impurities can be removed by forming this gaseous product as sulphur dioxide. Sometimes in roasting, student, the ore become highly porous. Once the ore becomes highly porous, means if it is consisting of what? Small holes, then further processing becomes very easy. As more pores, it increases the surface area of the ore particles. Roasting sometimes also involves self-reduction reaction. When you say self-reduction reaction, for some metals, let us understand what is self-reduction reactions. In science, we can say the reduction in which species reacts with itself. See, the product which is formed in the roasting starts reacting with itself to form a new species. For example, if you will see, in extraction of copper metal, student, since copper is obtained in the form of this ore, where this is the association of sulphur with copper, where copper, the charge of the copper is what? 1+. So it is called as copper 1 sulphide or cuprous sulphide. So during roasting, this metal sulphide is heated with the excess of air. So it gets converted to what? Metal oxide. Again, in this metal, if you'll see, copper is present in the form of 1 plus. So when copper 1 sulphide is roasted, it gets oxidized to copper oxide, and the sulfur dioxide gas, being gaseous product, it gets removed. Now this copper 1 oxide reacts with the remaining copper 1 sulphide which were not oxidized. We are not adding any external reducing agent. You can say this copper 1 sulphide which were present in the form of residue during roasting. This copper 1 sulphide immediately react with the formed copper 1 oxide. It removes oxygen. This oxygen part of copper 1 oxide combines with the sulfur part of copper 1 sulphide, and it forms what? Impure copper, and there is a release of what? Sulfur dioxide. So if you will see, the copper 1 oxide get reduced by its own product. So this copper 1 sulphide here is acting as self-reducing agent. It reduces copper 1 oxide into this copper. This copper is consisting of small amount of impurities, and there is presence of some blisters like structure onto its surface. That's why it is referred as blister copper. So actually blister copper is impure form of copper. It also happens in this other metals also. For example, mercuric sulfide. If mercuric sulfide is oxidized, it forms oxide of mercury as well as what? Sulfur. So we are getting mercuric oxide and sulfur dioxide. Sulfur dioxide being gaseous product, it gets removed. And this mercuric oxide which is formed, it again reacts with the residual mercuric sulfide which acts as the self-reducing agent. It removes the oxygen. So this oxygen of the mercuric oxide combines with the sulfur of the mercuric sulfide, and it forms impure mercury metal, and there is a loss of the gaseous product which is acting as what? A volatile impurities. Also in case of lead, student, if you will see, the same reaction take place if the lead sulphide, since it is the sulphide ore of the metal. So we carry out what? Roasting. During this, what happened? This oxygen combines with both the part, and it forms its corresponding oxide, and there is a loss of impurities in the form of sulfur dioxide gas. So this lead oxide which is formed again without adding any external reducing agent, this lead oxide combines with the lead sulphide which is the residual product, and this lead sulphide causes reduction or removal of oxygen of the lead oxide, and it forms impure lead metal, and there is a loss of the gaseous product which is acting as what? Volatile impurities. So in all these processes, if you will see, we are not adding any external reducing agent, but during the roasting process only the sulphide ore is acting as reducing agent, and it reduces oxide ore into what? Impure metal. So this type of processes sometimes takes place in roasting, which we refer as what? Self-reduction reactions. We are converting a metal compound to metal oxide in order to remove the impurities. Sometimes even after heating the metal compound or concentrated ore, all type of the impurities cannot be removed. So what we are supposed to do? Even after heating, even after doing roasting and calcination, if the concentrated ore contains what? Impurities. If the impurities are not removed only by simple heating, then in such cases we are adding some chemical substance which helps us to remove these impurities. So these chemical substance which helps us to remove the impurities from the concentrated ore is referred as what? Flux. Let us understand what is flux, student. Flux in science can be defined as, it is a chemical substance which is added to concentrated ore in order to remove gangue to form easily fusible slag. It's very important, student. Let us repeat it again. When I'm talking about flux, please remember flux is added to remove those type of impurities which cannot be removed by doing calcination and roasting. So flux, it's a chemical substance and it is added to the concentrated ore in order to remove the gangue to form easily fusible slag. If you'll see this general reaction, this gangue is actually present with what? Metal compound in the concentrated ore. But this gangue is very difficult to remove by simple heating. So we are adding what? Flux. So if you'll add flux with the concentrated ore, then this flux combines with the gangue and it forms easily fusible mass of the impurities. This easily fusible mass of the impurities is referred as what? Slag. The slag can be easily removed from the metal compounds. So flux, please remember this equation, flux combines with gangue and it forms easily fusible mass, and this easily fusible mass is referred as what? Slag. Let's take one example. Say for example, if the gangue or impurities which is present in the metal compound is oxide of iron. So this oxide of iron, since it is basic in nature, so we have to add acidic compound so that it can combine with that. So we are adding a flux known as SiO2, silica. So when the silica is added with this both combines and it forms easily fusible slag, which is referred as iron silicate. So this iron silicate can be easily removed from the reaction by heating. If you'll see principle of adding flux, student. So first we need to understand the concentrated ore that we have taken in the extraction process is consisting of ore which is consisting of metal compound along with certain impurities. But this impurities we are unable to remove only by simple heating. So what we add as a chemical substance? Flux. So when the flux is added to this mixture, then what is the role of this flux? Does flux combine with ore? Does flux combine with the impurities? So please remember, flux combines with the impurities, that is gangue, and it forms easily fusible mass. It's a type of chemical chain. When we are saying it's a easily fusible mass, means its melting point is very low, and that's why even by low heating we can easily remove it. So the slag can be removed and the left residual part is what? Ore. This slag can be easily removed because its melting point is very low. So flux, if we want to understand, student, what type of the flux can be used in a chemical reaction? So it totally depends upon the nature of the gangue particle. So on the basis of the nature of the gangue particle, the flux can be classified into two ways. One is referred as what? Acidic flux, and one is referred as what? Basic flux. Before using any type of flux, if you will see, so acidic and basic flux is added in the extraction process only by knowing the nature of gangue. Say for example, when to use acidic flux. Now suppose if the concentrated ore I have taken is what? Zinc sulphide, and this zinc sulphide is the metal compound which is the ore of zinc metal. Along with the zinc sulphide, if you will see, it is consisting of impurities calcium oxide. Now we know that, student, the calcium oxide is the oxide of calcium, which is a metal, and metal oxides are generally basic in nature. So if I have to remove base, then as per neutralization reaction I have to add what? Acid. So I need acidic flux. So the question is that when to add acidic flux? Acidic flux is added only if the gangue is what? Basic in nature. Since here the gangue is basic in nature, calcium oxide, so we are adding acidic flux, and this acidic flux is what? Silica. So when the silica is added to the powdered mixture of this and heated, so silica will not combine with the zinc sulphide, it will combine with the calcium oxide. So if it combines with the calcium oxide, it forms easily fusible mass of calcium silicate, which can be easily removed because it is obtained in the molten form, which is referred as what? Slag, and we can remove this gangue from the ore, that is zinc sulphide. So here we understood when to use acidic flux. Again, student, if the metal oxide or the gangue is what? Basic in nature. So can I say here the silica is acting as acidic flux? Now the question is that when to use basic flux. Student, we can use basic flux only if the gang which is present is what? Acidic. If you will see, suppose if the zinc sulphide is consisting of silica as an ore. If you must have seen in the previous cases where the zinc sulphide was associated with the oxide of calcium, but sometimes zinc sulphide is associated with the silica as an ore. Now the silica is what? Acidic compound, and to remove acidic compound we have to add what? Basic compound. So here we have to add basic flux. So basic flux we can take example as what? Calcium carbonate. So when you will add calcium carbonate and if you will heat this mixture, so this flux will not combine with the zinc sulphide, it will combine with what? Silica. Because this flux we have taken is what? Basic in nature, and the basic substance is combined with what? Acidic gang. So this calcium carbonate will combine with the silica and it is going to form a easily fusible mass of molten compound which is referred as calcium silicate, and it is going to give mixture of zinc oxide and carbon dioxide. This carbon dioxide being gaseous product, it can be easily removed from the mixture and we will get zinc sulphide, the metal compound, free from this. Got this? So we understood when we are doing extraction, that is the second part of the metallurgy. We are converting a metal compound to metal oxide, and for that process we do roasting and calcination. Student, roasting and calcination we are doing to convert metal compound to what? Metal oxide. So if you just find out the difference between roasting and calcination, let's say this point is what? Roasting, and this point is what? Calcination. So roasting, if you will see, ore is heated to very high temperature, but again this high temperature should be below that the melting point of the compound in presence of excess of air, and ore is heated in absence of air in limited supply of air. Do you know which type of ore we are taking for roasting and calcination? Yes, sulphide ore. If you see, if the sulphur is associated as an impurity, so all sulphide ore are oxidized to what? Metal oxide. Basically, if you will see, this metal sulphide, the conversion of metal sulphide to metal oxide is referred as what? Roasting. And in case of calcination, we take hydrated ore, or generally we take what? Carbonate ore. So this carbonate ore is heated, which release carbon dioxide, and it gets converted to what? Metal oxide. So in both the processes, we are converting metal compound to metal oxide. The basis of above discussion of the extraction, what we have discussed, all of you, please you try to solve these questions which I have given. The first one is what? Match the following, and the second one is what? True and false. So all of you, please just pause the video, take your time, 2 to 3 minutes, and solve it. And after 2 to 3 minutes, I will just explain you the answer of this. Come on, start doing it. Just pause your video and solve it. Don't check the answer. Yeah. Okay. Let us check the answer. If you see this, they have given different terms here, student, like roasting, calcination, acidic flux, and the basic flux. And at this side, they have given the formula. So clearly, we all have to identify the example of these terms. Now we know that roasting is one method of extraction, and this is applied for metal sulphide. So the answer should be what? Zinc sulphide. Zinc sulphide is taken as in roasting, and the zinc sulphide gets converted to what? Zinc oxide. Calcination is carried out for carbonate ore, or we can also take it as for hydrated ore. So here the hydrated ore is what, Al2O3.2H2, which is referred as what, bauxite. Now flux is a chemical substance which is added to remove gangue by forming a easily fusible mass, which we referred as what, slag. So there are two type of the flux we are using. Acidic flux, if you will see. So acidic flux is what, silica, and the basic flux we are using is what, calcium oxide. Now about true and false, if you see the very first statement what they have given, roasting is carried out for carbonate ore. No, it's false. Roasting is carried out for sulphide ore. Second, if you will see, in calcination and roasting, concentrated ore is heated above its melting point. No, it's false. We cannot heat concentrated ore above its melting point because it will start burning, and we prevent burning of the substance. So this can be achieved only by lowering the temperature, or the temperature should be below the melting point. Third, if you will see, in calcination, carbonate decomposes to oxide. Yes, it is true. Calcination is generally employed for ores containing metal carbonates and hydrated metal oxide. Yes, this is the characteristic of the calcination, and it is a true statement. Roasting and calcination is carried out in the blast furnace. No, the question is wrong here, because we are using blast furnace for the extraction of iron metal, and for roasting and calcination we are using reverberatory furnace. Layer of reverberatory furnace is made up of silicon carbide. Yes, silicon carbide is a refractory material. When we say refractory material, means what? It can withstand with very higher temperature. So this statement should be what? True. Now let us try to solve the another worksheet here. All of you pause your video for 3 to 4 minutes and read all the statement properly and answer the appropriate word which comes here. After 2 to 3 minutes, I will give you the answer of this. Come on, try it. Just pause your video and solve. Don't search for the answer. Come on. Yeah. So, the appropriate word for the first statement, if you'll see, student, the process of conversion of metal sulphide to its oxide. Metal sulphide, you know, metal sulphide to its oxide, this process should be, yeah, the word should be what? Roasting. Please check your answer. Is it correct? Yes. Second, if you will see, dash substances which is added to concentrated ore during smelting to remove gangue is called dash. Can I say it can be any chemical substance? Chemical substances which is added to concentrated ore during smelting to remove gangue is called flux. The answer is flux over here. Dash substance act as gangue as well as flux. This substance is what? Silica. Silica can act as gangue as well as what? Flux. Very important point. Next question, if you'll see, the fourth one, the waste product formed by combination of flux and gangue. Any idea what it is called? Yes, it is called as easily fusible mass, which in the scientific language we say as what? Slag. Fifth says that to remove silica gangue, dash flux like dash is added. So the flux, addition of flux depends upon the nature of this. Silica is what? Acidic. So we have to add basic flux, and the basic flux generally we take metal oxide like calcium oxide. Silica reacts with the calcium oxide to form fusible slag as calcium silicate. So the formula of calcium silicate is CaSiO3. Here we got the answer of 6. Let's check the 7th one. If an ore contains basic impurities like calcium oxide, then we have to add acidic flux. See, acidic flux. So this acidic flux which is added is silica, because in the third case if you will say Silica can be acting as what? Gangue as well as what? Flux. The gaseous product given out in roasting is. Now, roasting is carried out for metal sulphide. So, when we are heating metal sulphide in the excess, we get sulfur dioxide gas. Generally, when flux combines with gangue, it forms easily fusible mass and which is referred as what? Slag. See, FeO, if it combines with SiO2, so it forms iron silicate as well. And this iron silicate slag has the formula of FeSiO3. Calcium carbonate is formed by the combination of calcium oxide and CO2. Now we all know that extraction is consisting of two methods, and in these two methods, if you'll see, the common process which takes place is for oxidation, where we are converting this metal compound to metal oxide. But we don't want metal oxide, we want metal in the free form. Then why we are converting to metal oxide? Because it is easy to obtain free metal from its metal oxide. Now this process of getting free metal from the metal oxide which is obtained in the extraction is referred as what? Reduction. But before this, if you will see, this metal compound is converted to metal oxide by a process of what? Oxidation. And now we just learned that in oxidation we apply two different methods. It depends upon the nature of the reactivity of the metal compounds. If the metal compound is present in the form of carbonate, then we heat that metal compound in the limited supply of air. Now, if the metal compound is present in the form of sulphur, we heat metal compound in the excess of air. See, metal compound, if it is heated in the limited supply of air and converted to metal oxide, this process in science is referred as calcination. And generally the calcination is applied for carbonate ore of the metal. But if the metal compound is converted to metal oxide and by heating in excess of air, this process in science is referred as roasting. So calcination and roasting, in both the processes we are converting metal compound to metal oxide. Once we got the metal oxide, in order to remove oxygen part from the metal oxide to get free metal, we are doing what? Reduction. So now we will discuss about what? Reduction and the various types of the reductions. Student, reduction depends upon the reactivity of the metal. Generally, reduction which is applied is of two types. One, by using suitable chemical reagent. This method is referred as chemical reduction. And by using a principle of electrolysis for highly reactive metal, this method is referred as electrolytic reduction. Under chemical reduction, if you will see, if the reduction is carried out by making aqueous solution of the metal, that is referred as hydrometallurgy. And again in the chemical reduction only, if the reduction is done by heating process, then this process is referred as what? Pyrometallurgy. For very high reactive metals, we are using the principle of electrolysis, and this method is referred as what? Electrolytic reduction. So one by one we will study about all type of what? Reductions. So reduction method is basically used to extract pure metal, you can say, from its metal oxide which is obtained by calcination and roasting. So depending upon the reactivity of the metal, the reduction can be basically classified into two types. One is chemical reduction and one is what? Electrolytic reduction. Now this classification is totally based upon the reactivity of the metals. In case of chemical reduction, we apply this method for less reactive metals, and for highly reactive metals we apply what? Electrolytic reduction. Student, in chemical reduction, again it is classified into two methods. If the reduction is carried out in the aqueous solution by making aqueous solution of the metal and we add some suitable reagent to recover the metal, that process is referred as what? Hydrometallurgy. But in chemical reduction, the metal is obtained simply by heating metal oxide by using some suitable reducing agent, then that process is called as what? Pyrometallurgy. And in electrolytic reduction, we apply principle of electrolysis, and this is applied for highly reactive metals. So let us understand the very first one, hydrometallurgy. Let's see that what we do in the hydrometallurgy. Generally, hydrometallurgy is applied for less reactive metals, and it is used to extract metal from aqueous solution of their salts. Let's say the metal which is over here is less reactive metal, and we will take example of less reactive metal as silver and gold. So this is consisting of impurities. So the metal which is represented over here is what? Impure metal. It is consisting of some amount of impurities. So we are making aqueous solution of their salts. If you'll see, the water is acting as what? Medium. That's why the word is referred aqueous. We are passing air where the oxygen is going to act as what? Oxidizing agent. It oxidizes metal to its ion into the aqueous solution, and we are adding any chemical reagent which is consisting of Cn minus ion. Here the Cn minus ion actually provide what? Complexing agent. So when you say complexing agent, so this Cn minus ion helps to react with this less reactive metal, and it forms water soluble complex. This water soluble complex which is formed between metal and cyanide can be represented like this. Here if you will see, it is the soluble cyano complex of the metal. Please remember, the metal is present in the form of complex, but we don't require this associated form of the metal. We require what? Free metals. So to obtain free metal, we have to add another metal which should be more reactive than this metal in order to follow metal-metal displacement reaction. If the metal is what? Silver and the gold, then generally we add what? Zinc, and zinc is more reactive as compared to silver and gold. So zinc being more reactive, it displaces metal from its complex in the aqueous solution. So in this case we get what? Precipitate of the metal, and the zinc which is more electropositive, more reactive, which is acting as a reducing agent, forms complex with this and remain soluble and remains in the solution only. So this is how we do hydrometallurgy. So in science, when we talk about hydrometallurgy, we can say it is a process of extraction of metals by converting their ores into aqueous solution salt of the metal. Like if you will see, here we have converted metal to its aqueous solution of the salt, like cyano complex which was soluble in the solution. So what we are doing here, the process of extraction of metal by converting their ores into aqueous solution of the metal compound, and then we are reducing of this solution using suitable reducing agent. Like zinc is the metal which we have added to reduce this silver and the gold metal. So basically hydrometallurgy involves two steps. The very first step, we are forming what? Soluble cyano complex of the metal, and the second step involves removal of the metal from its cyano complex by adding what? More reactive metal or highly electropositive metals. So within the chemical reduction, after learning the hydrometallurgy, there is another method which involves heating of the metal oxide, and sometimes the metal oxide is heated along with some suitable reducing agent. Depends upon the reactivity of the metal oxide. So this process is referred as what? Pyrometallurgy. So let's talk about this pyrometallurgy. Student, in pyrometallurgy, which is basically applied for metals of medium reactivity. The ore is reduced to metal using high temperature. Now this temperature, if you'll see, this temperature may be above than the melting point of the metal. That's why sometimes we are getting what? Vapor of the metal, and that vapor of the metal is condensed to get back liquid metal, and that is condensed to give what? Solid. So pyrometallurgy, if you'll see, this pyro means what? Heating, and this is a strong heating of the metal oxide by using suitable reducing agent if it is required. It depends upon the reactivity of the metal. In science, you can say pyrometallurgy is a process in which the concentrated ore are reduced to form crude metal at high temperature. So again, the metal that we are getting from the metal oxide, even in the pyrometallurgy, that is a reduction process, the metal is not completely pure. It is consisting of still some kind of impurities, which we referred as what? Crude metal. So here the crude metal means what? It is what? Impure metal. And here if you will see the word, the metal oxide is heated at very high temperature, and this temperature may be above than melting point of the metal. If metal oxide is not giving metal on heating, so to remove metal from its oxide, we are using what? Reducing agent like carbon. It can be what? Hydrogen, or it can be what? Aluminium. These selection of reducing agent, it totally depends upon the stability of the metal oxide. But if you are heating metal oxide with these reducing agent, then these are referred as what? Smelting. In some cases, if the carbon is used as reducing agent, it is referred as carbon reduction process. So pyrometallurgy also involves a process of smelting. So smelting in science can be defined as it's a process of extracting the impure metal. Again, there is a word we are using, impure metal. It can be a crude metal from its ore at high temperature using carbon or any other suitable reducing agent. Student, in this case, actually what happens, if the metal oxide is very highly stable, then it is very difficult to remove oxygen from it. So in order to remove oxygen, we are heating the metal at very high temperature along with some reducing agent. Most common is what? Carbon. That's why this process is also referred as carbon reduction process, or what? Smelting. If you'll see these examples, like if you'll see, this is cassiterite. Cassiterite is the ore of what? Tin. Here if you'll see, tin is associated with the oxygen. So this oxygen cannot be simply removed by heating. So we are heating this cassiterite with the reducing agent as what? Carbon. Now what is the role of this carbon? This carbon removes this oxygen and it forms a gaseous product. So this gaseous product can be easily removed and it forms what? Vapors of what? Tin. So this vapor of tin is condensed and we get back what? Solid metal. But this metal which is obtained is what? Impure metal. Similarly, in this case, if you see, in Fe2O3, again we want to remove this oxygen. So here the reducing agent which is used is what? Carbon monoxide. Yes, carbon and carbon monoxide can be used as what? Reducing agent. So here if you see, carbon monoxide removes this oxygen, like carbon removes oxygen here, and it forms a gaseous product which can be removed, and it gives the residue of what? Iron metal. So these are the examples of what? Smelting, where we are getting impure metal or crude metal from its oxide when that oxide is heated with reducing agent at very high temperature. Move to another method of reduction. Now this method of reduction that we referred as what? Electrolytic reduction. Student, here if you'll see, the word that is used is electrolytic because it involves the principle of what? Electrolysis. So when we are carrying out electrolytic reduction, specifically in science, it is referred as what? Electrometallurgy. Generally, student, electrometallurgy is applied for highly reactive metal, which involves electrolysis of their molten salts. Say for example, It can also involve electrolytic reduction of what metal compounds. If the metal is present in the form of their oxides, hydroxides or halides. So the metal compound which is taken in the form of hydroxides, oxides and halides are taken into the molten state, or you can say fused state. So fused or molten state of the salt of these metals are electrolyzed, and from there the pure metals are extracted. The metals which are obtained here are always obtained in the pure form. They don't need to be refined again. The best example we can take is what? Extraction of sodium metal. Students, extraction of sodium metal is carried out from its salt, and the salt is what? Sodium chloride, which is also referred as common salt, table salt or rock salt. So sodium chloride, if you will see, the physical state of sodium chloride is what? Solid. It is hard and brittle solid, and the constituent particles of the salt, if you will say, it is metal and non-metal, which is intact with each other by forming strong electrovalent bond. So when the solid is heated about 800 degrees Celsius, it forms what? Molten state. In the molten state, the bond, the stronger bond which is present between metal and non-metal breaks, and it forms its constituent ions. These ions undergoes redox reaction to their respective electrode, and they produces their product. In case of fused NaCl, when the electrolysis is carried out, we are getting deposition of the sodium metal at cathode, and there's evolution of the chlorine gas at what? Anode. If you'll see, this entire process is carried out in Dodge cell, which is apparatus used for electrolysis of NaCl. In this apparatus, if you'll see, we are taking molten NaCl, and this molten NaCl is consisting of Na plus and Cl minus ion. This is carried out by using graphite electrodes. So Na plus, being it is positive charge, it gets attracted to negative electrode, which is referred as what? Cathode. So it gains electron, undergoes reduction, it gets reduced, and it forms sodium metal. This sodium metal gets deposited onto what? Cathode. Its opposite ions, that Cl minus, since it is having negative charge, it gets attracted to what? Anode, which is made up of what? Carbon, that is graphite, one of the allotrope of the carbon. So this Cl minus loses electrons, and it gives a gaseous product which evolve at what? Anode. So this is the way that how we extract sodium metal from its salt in the molten state. So this process is the example of electrometallurgy. So before we proceed further, let us solve the worksheet, which is based upon the previous topics that we have discussed. Now it is consisting of some match the columns type of the question and also true and false. So student, you just pause the video for 3 to 4 minutes and get the correct answer of all these. Once you'll get the correct answer of all this, then I can discuss these all answer with you. So come on, start solving it. Yes. So let us check the answer. The very first part, if you'll see in the column 1, they have given explanation about the different method of reduction, and in column 2 they have given what type of the reduction or some specific chemical reagents. So in order to solve this, first we will understand the meaning of this statement. For example, the very first one, if you will see, it's a process of extraction involve heating of the metal oxide. If you able to recollect, then in which process we are using what heating? Yes, the process of extraction which involve heating of the metal oxide ore is actually consisting of what? Pyrometallurgy. When you say pyro, so pyro means it is the process of strong heating. The second statement, if you will see, it is extraction involve formation of aqueous solution of metal, and it's recovered by adding more reactive metals. Such type of the process is carried out in hydrometallurgy. So the answer is against it. You can see. Third question they have asked is method of reduction involve principle of electrolysis. So electrolysis is used generally for highly reactive metal, and this process is referred as what? Electrometallurgy. Fourth, they have asked chemical used for the extraction of gold and silver. Basically, gold and silver, they are subjected for the hydrometallurgy and they are allowed to form cyanocomplex. So the complexing agent that we take is what? Aqueous sodium cyanide solution. Hope you have got the correct answer. Now let's move to the true and false. Let's check the very first statement. In the very first statement, they have talked about hydrometallurgy is used for the extraction of sodium metal. So this statement is false. Hydrometallurgy is basically used for what? Less reactive metal, and this less reactive metal can be gold and silver. We don't use for sodium metal. In the extraction of the sodium metal, we use what? Electrometallurgy. Second thing they have asked is pyrometallurgy involves heating of metal oxide with a suitable reducing agent. Yes, this process can also be said as what? Smelting. So this is correct statement. Carbon and carbon monoxide used as oxidizing agent in the extraction process. No, it is false statement, because carbon and carbon dioxide cannot be used as oxidizing agent. It is used as what? Reducing agent. In aluminothermite process, the reducing agent is used as what? Aluminium. In this case, what happens? If you'll see, there are certain reaction. For example, in pyrolusite, which is the ore of Mn, if you'll see, if we are going to mix with the aluminium, then this aluminium displaces, aluminium being highly reactive, it just displaces what? Manganese, and it forms Al2O3, and it gives what? Manganese metal. In this, a large amount of heat is given out, so the metal which is obtained is in the molten state. This process is called as what? Aluminothermite process, and here the aluminium acts as what? Reducing agent. Similarly, it also takes place in the case of iron. Fe2O3, we take what? Aluminium. Aluminium being more reactive with the iron, it displaces iron, and here it again forms Al2O3, and there is a formation of molten Fe, and during this process a large amount of heat is given out. Generally, this process is having importance of filling and welding of what? Railway tracks. So aluminium in this process, they have asked, is used as what? Reducing agent. So the statement is what? True. The process of removing impurities from ore is called as reduction. No, reduction is carried out to remove oxide of the metal to convert what? Crude metal. So this process should be what? Concentration, and this is false. Metal leached by cyanide process is zinc. No. Mostly we use what? Silver and gold metal for the extraction. Now let us try to solve the another worksheet, student, over here. It is also based upon the previous discussion of the extraction. Now this is consisting of the various question, and the demand of the question is to fill the appropriate answer onto this. So all of you please go through with the statement properly and try to find out the correct answer or appropriate answer of this. Come on, you can pause this video and you can refer these all questions, and please you try to write the correct answer of each statement. Come on, try it. So if you will see, when we talk about the first statement, they have asked method used for the reduction. So generally method used for the reduction depends upon the reactivity of the metal, and generally we use three methods. If you will see, one is hydrometallurgy. Yes, we also use pyrometallurgy and electrometallurgy. So there are three methods we are using. The very first is what hydrometallurgy, pyrometallurgy and the electrometallurgy, depending upon the reactivity of the metals. These all methods are the different methods of reductions. Second, if you will see, the process of extraction of metal by converting their ore into aqueous salt solution of metal compounds and reducing them by suitable reducing agent. This type of the process is carried out in hydrometallurgy. So the answer should be for hydrometallurgy. Okay. Third, if you'll see, for extraction of highly electropositive metals like sodium, potassium, magnesium, calcium and aluminium, dash process is used. The process which is used for highly electropositive metals are actually electrolysis, and this is referred as electrometallurgy. Fourth, the products obtained during electrolysis of molten NaCl at cathode and anode. So at cathode we are getting what? Liquid sodium metal which gets deposited onto the surface of the cathode, and there is an evolution of greenish yellow color gas onto the surface of anode. Method of reduction involves strong heating of their metal oxide. So this method should be what? Pyrometallurgy. Heating of metal oxide along with suitable reducing agent is called as, yes, this process we referred as what? Smelting. Seventh, if you'll see, dash as reducing agent involve carbon reduction process. You can say carbon. Here the carbon is used as reducing agent, and if carbon is used as reducing agent, generally that process is referred as carbon reduction process. In 8th, if you see, silver and gold present in their ores are dissolved in dash solution. We dissolve into aqueous sodium cyanide solution which forms cyano complex, and here the air is acting as what? Oxidizing agent. This soluble complex, by adding reactive metals like we add zinc metal. So being zinc metal is more reactive, it displaces what? Silver and gold from its cyano complex. Process involve heating of concentrated ore to reduce metal oxide to metal. Again, let's see. Process involve heating of concentrated ore to reduce metal oxide to metal. Is reduction. Yes. And in metallurgical process, coke is used as, you can say it is reducing agent. So please check the answer. Extraction step. We had converted metal compound to metal oxide, but we don't want metal oxide, student. We want what? Metal. So next step that we are going to study is what? Involve removal of oxygen from the metal oxide to form crude metal. So basically we refer it as what? Reduction method. And in all these type of reduction method, which is totally decided upon the reactivity of the metal, this reduction of metal oxide to metal can generally shown by this general equation. You can see onto the left hand side there is a metal oxide. This metal is associated with the oxygen, and actually we don't want this metal oxide, we require what? Crude metal. So it is very important for us to remove this oxygen part from the metal. Now this removal of oxygen is not so easy as we think. This removal of oxygen totally depends upon the reactivity of the metal. Sometimes we have to add some foreign substances like carbon and carbon monoxide, which acts as what? Reducing agent. When these substances are added with this, in both the cases it requires strong heating. So the oxygen leaves this metal and it gets combined with the carbon and carbon monoxide, which acts as reducing agent, and it gives what? Free metal. Again, this metal which is obtained in this process is not pure metal. It's what containing some amount of impurities, which is referred as what crude metal. So during this process, you will find there are certain metals which can be reduced easily even after heating. So some metal oxides gets reduced very easy, while some metals, if the metals are very reactive, they are not ready to lose this oxygen easily even after using reducing agent. So if metal is more reactive, it is very difficult to reduce its oxide. In both the cases, whether you will take less reactive metal oxides or more reactive metal oxides, in both the cases of reduction, we require what? Heating. So it is very important for us to know the variation of temperature and the feasibility of the reaction. So basically in science, you will see the study of variation of temperature during thermal reduction, we refer it as what? Pyrometallurgy. So whenever we carry out pyrometallurgy, always we take the help of what? Thermodynamic concepts. These thermodynamic concepts helps us to make the process easy, and it also helps us to find out the exact temperature at which we can carry out the reduction process, and also they helps us to find out the exact and suitable reducing agents. So in order to understand, we have to understand the basic terminology and basic parameters which involved in the thermodynamic concepts. We take Gibbs energy as the basis of this principle. So Gibbs energy in science, basically we can explain like this. It is the energy associated with a chemical reaction that can be used to do work. Generally in science, if you will see, this Gibbs energy or change in Gibbs free energy, which is referred as what? Delta G, at specific temperature and pressure, can be represented by this simple formula where you can say it's a delta G. Again, I'm saying delta G is what? It's Gibbs free energy, change in Gibbs free energy, which depends upon two parameters, that is delta H and delta S. And here the T is indicating temperature on Kelvin scale. So delta H is actually indicating enthalpy change of the system, and delta S is referred as entropy change of the system. There is a difference between these two terms, student. If you see, delta H we refer as what? Enthalpy change of system, and delta S we will refer as what? Entropy change of system. These two terms we will learn in detail in the chapter called thermodynamics. For time being, we are discussing only the basic explanation. So delta H is enthalpy change of the system. Delta S is what? Entropy change of the system, which is also related with the randomness of the system. When we say any reaction is what? Spontaneous. Basically delta G values are indicating spontaneity and the feasibility of the reaction. So in order to understand or to say whenever any reaction is what? Spontaneous, then the delta G value should be negative. It's a point to be noted. For the spontaneous or for the feasible reaction, the delta G value should be negative. So in the given equation, if you will see, where the equation says that delta G is equal to delta H minus T delta S, the delta G has to be what? Negative, and this negative value actually indicates feasibility of the reaction. So the value of the delta G versus temperature explains the idea of governing the reaction and selection of suitable reducing agent. So this can be explained on the basis of what? One graph which referred as what? Ellingham diagram. So Ellingham diagram basically based upon the principle of what? Thermodynamics, which actually helps us to understand the spontaneity of the reactions. And for this, we should know the difference of two parameters, delta H that we referred as what? Change in enthalpy, and delta S which is referred as what? Change in entropy. So by Knowing the values of delta H and delta S, we can calculate delta G, which is referred as what? Change in Gibbs free energy. So if you'll see the formula which is given in science, delta G is equal to, it is the difference of delta H minus delta T delta S. Here the T is indicating what? Temperature. So in this, if you just substitute the value of delta H and delta S of any reactions, so the reaction can be spontaneous or can be feasible only if the delta G value is what? Negative. So before going into the detail about Ellingham diagram, now let us understand certain basics of the thermodynamic principle, which is going to help us to understand the reduction process. Now in basic science, if you'll see, there is a term that we have used, that is delta G, which is called as Gibbs free energy. This delta G can be calculated by this equation, which is referred as Gibbs-Helmholtz equation. So this is the way that we can represent Gibbs-Helmholtz equation, and this equation is in the form of like delta G is equal to delta H minus T delta S. So here if you'll see, delta G is referred as what? Gibbs free energy. Delta H is referred as change in enthalpy. T is the parameter which is temperature on Kelvin scale, and delta S is indicating what? Randomness of the system, which is also said that entropy. So by applying or substituting the values of delta H and delta S into this equation, there can be three different values of the delta G which describe the type of the reaction. In case if the delta G is negative, then that reaction is referred as what? Spontaneous reaction. I repeat, if the delta G value comes negative, then that reaction is what? Spontaneous. If the value of the delta G is what? Positive, then that reaction is not feasible, and that is non-spontaneous reaction. So basically spontaneity and the non-spontaneity can be described by taking the values of delta G and by checking the charge. If the delta G comes negative value, the reaction is referred as spontaneous, and if the delta G comes as the positive value, it is referred as what? Non-spontaneous. In case if the delta G comes 0, then we refer the system is at equilibrium. So in order to understand the different values, if you will see, I have given 4 different cases, and in all the cases, if you check the sign of delta H and delta S, in the very first case, if you'll see, the delta H value are indicated into what? Positive. So when you say positive, means the process is what? Endothermic. And when you say delta S is positive, means the randomness of the system increases. Now the detail of all these parameters, student, we are going to learn in a chapter called thermodynamics. So we are just going to discuss only the basic part of it. So in the first case, if you'll see, where the delta H value is positive and the process is endothermic, and the delta S value is also positive, which indicates the randomness of the system increases. So let's say delta H is plus X and delta S is plus Y. In the second case, if you'll see, the delta H value is what? Negative. I have taken minus X, and here the delta S value is taken as what? Minus Y. So if I am saying delta H is what? Minus, it clearly indicates the process is exothermic, and delta S is negative, means the randomness of the system decreases. In third case, delta H is having positive values and delta S is having negative value. So in third case, delta H is for endothermic reaction and delta S is for the reaction where the randomness of the system decreases. In case of delta H, case 4, if you'll see, the delta H is what? Negative and the delta S is was positive. So here the reaction is exothermic and here the randomness what? Increases. So by considering all these cases, if the value of the delta H and the delta S is substituted, we can predict the value of what? Delta G, and we can predict the nature of the reaction which occurs. In the very first case, let's take this Gibbs-Helmholtz equation, which is delta G is equal to delta H minus T delta S. If I am substituting the value of delta H and delta S, if you will see, delta H in first case is plus X and delta S is what, plus Y. So if you are substituting this value, please remember we want to make this reaction spontaneous. So to make this reaction spontaneous, the delta G should be what, negative. So in order to make delta G negative, we have to change this variable parameter, which we say as what, temperature. So here the value of delta H is positive and the delta S is what, positive. So if you calculate, so it gives X minus Ty. Now what we are supposed to do in order to get delta G negative? So we have to increase the value of what, temperature. If you increase the value of the temperature, the value of Ty will increase and it will become what, bigger value. So if you are subtracting bigger value from the smaller value, automatically the value will be what, negative. So when delta H is plus X and delta S is plus Y, or you can say when the delta H and delta S both are positive, then the reaction can be made spontaneous at high temperature. You got this? In second case, if I am substituting the value in the same Gibbs-Helmholtz equation, here the delta H is minus X and delta S is what, minus Y. So if you will substitute it, delta H remains minus X, but here minus and minus it will become plus. So in order to make delta G negative, we want delta G negative because we want to make the process what, spontaneous. The temperature should be what, low. The reason is that if you will decrease the temperature, then the value of entire this Ty will decrease. So if you are adding lower value to this negative value, then you will get negative value of the delta G. So delta G can be made negative at low temperature, and if the delta G is negative, student, then the reaction will be what, spontaneous. In third case, if I am substituting the value, so delta H will be plus X and delta S is minus Y. So if you will see here, the values X as well as this Ty both becomes what, positive. So in all the cases, whether you will increase the temperature or decrease the temperature, the delta G will be what, positive. Now there is a limit to decrease in the temperature because the temperature is taken onto the Kelvin scale. So we cannot take into what, negative. So the value of the temperature has to be positive. And if the value of the temperature is what, positive, then the delta G value will come what, positive. So this reaction is always non-spontaneous at all temperature. Fourth case, if you'll see, where the delta H is what, minus X I have substituted and delta S is what, plus Y. So in this case, if you'll see, both the factors are what, minus. So if you'll solve this mathematically, you will always get the negative value for the delta G. Okay, so this delta G value, since it is coming negative, so this reaction will be spontaneous at all temperature. Of metal oxide during extraction process, if you'll see, the metal or the metal compound which is present in the ore, when it is heated in excess of air or limited supply of air, so in that case what happens, the metal which is present in the compound gets oxidized and form what, metal oxide. You can see the metal is present in the solid state and it easily gets combined to what, oxygen. This oxygen is acting as oxidizing agent. It causes oxidation of the metal and it produces product metal oxide. Generally, this reaction of conversion of metal to metal oxide is referred as oxidation, and this process is a type of combustion reaction. During this process, what happens? Some amount of heat energy is released. So since this process is what, combustion, and if the heat energy is released, so the process should be taken as what, exothermic. So all combustion reaction release what, heat, and all combustion reaction is a type of exothermic reaction. And for all exothermic reaction, the change in enthalpy, if you will see, the delta H always come as what, negative. So again I repeat, this metal combustion reaction, metal solid gets converted to what? Metal oxide, and this formation of the metal oxide releases some amount of heat. Since the heat is released, that's why this process is what? Exothermic. And for all exothermic reaction, if you'll see, the delta H value is what? Negative. To predict the value of delta S, we have to check the physical state of the reactant and the product. If you'll see here, the oxygen is what? It's present in the gaseous form. But in the metal oxide, when this oxygen combines with the metal and gets converted to what? Metal oxide, the physical state is what? Solid. So please remember, student, if the gas is converted to what? Solid, then the randomness of the gas molecule, or you can say the randomness of the system, decreases. Since there is decrease in the randomness, that's why the delta S should be what? Negative. Now we know that Gibbs-Helmholtz equation. If you see the Gibbs-Helmholtz equation, condition number 2, or you can say case number 2, where delta G depends upon the delta H and delta S, and here the temperature is taken onto the Kelvin scale. So for the above reaction, for combustion of the metal, the value of the delta H we are finding is what? Negative, as well as the value of delta S is also what? Negative. So if you want to make delta G negative, to make the reaction spontaneous, the temperature value should be what? Low. In case if you will increase the temperature, then what will happen? The value of the temperature will increase, so it will change the value of what? Delta S. So the delta G at high temperature in this case will become positive, and if the delta G will become positive, then the reaction will become what? Non-spontaneous. But at low temperature, if you will see, delta G value is what? Negative. So in order to form metal oxide from metal, the delta G value should be what? Negative. If the delta G value is what? Negative, then the temperature should be what? Low. So we can say that formation of metal oxide favors at low temperature. Now in case of formation of carbon monoxide, basically in the formation of carbon monoxide, we take powdered form of the coke. Coke is one of the allotrope of the carbon, and the physical state of this coke is what? Solid. So this powdered form of the coke, when it is heated into what? Oxygen. This oxygen is acting as an oxidizing agent. If the limited supply of the oxygen is allowed, then this oxygen combines with the carbon and it forms gaseous product, which is carbon monoxide. Now if you will see, this process is what? Oxidation, and also it is a process of combustion. Just now I have told you the combustion is a type of what? Exothermic reaction. So for all exothermic reaction, the delta H value that we see change in enthalpy is what? Negative. So if it is a type of exothermic reaction, then delta H value of this reaction should be what? Negative. Means during this some amount of heat will release. Now in order to find out delta S, we have to check the physical state of the reactant and the product. For oxygen, if you will see, the physical state is what? Gas, and for carbon monoxide, the physical state is what? Gas. But both the reactant and the product, both are gases, student. But if you will see, the number of mole of the reactant, gaseous reactant, and the number of mole of the gaseous product is different. On to the left hand side, if you will see, there is 1 mole of the gas, and which is converting into what? 2 mole of the gas. So basically the number of the mole of the gas increases. So if the number of the mole of the gas increases, then that system indicates there is increase in the randomness. So the delta H value should be what? Positive. So in Gibbs-Helmholtz equation, if I am just going to substitute the value of delta H and delta S, then I will get it like this. Like delta H will be what? It's minus value and minus T, and this will be what? Delta S is having what? The positive values. So in order to make delta G negative, what should be done with the temperature? Yes, any guesses? This formation of carbon monoxide should take place at lower temperature or higher temperature. Yes, the answer should be what? Higher temperature, because if you will increase the value of the temperature, so this entire term will increase, and if this entire term will increase, then if you will subtract this bigger value from the smaller value of the delta G, you will get negative value of the delta G. So delta G is what? Negative in this case if the temperature is what? Higher. So it clearly indicates formation of carbon monoxide takes place at very high temperature. Look at this. Delta G decreases if increase in temperature. That's why we say the formation of carbon monoxide favors at high temperature, because at high temperature the delta G value what? Decreases. This case is the formation of carbon dioxide. In the earlier cases we had seen that formation of the metal oxide and the formation of carbon monoxide. So what happened in the change in the parameters in the Gibbs-Helmholtz equation when the carbon dioxide forms? In order to form carbon dioxide, again we are taking powdered form of the coke, which is one of the allotrope of carbon, and this powdered form of the coke is now heated in excess of air. So if the carbon is heated in the limited supply of air, there was formation of what? Carbon monoxide. But if the carbon is heated in the excess of air, if you will see, then this form carbon dioxide. Again, if you will see, this process is oxidation, and again it is a type of combustion reaction. Just how I had told, all type of combustion reaction, since it releases what? Heat energy. So this process should be what? Exothermic. And as per thermodynamics, all exothermic reaction, the delta H value should be what? Negative. Now in order to decide delta S, student, we have to check the physical state. So the reactant, that is oxygen, if you will see, the physical state is what? Gas. And this oxygen converts into what? Carbon dioxide, which is also a gas. If both the physical state are gases, then we generally check the number of mole of the gases onto the reactant side and the product side. So onto the left hand side, if you will see, the number of mole of this oxygen is what? 1 mole. And here if you will see, the product which is formed is also 1 mole. Let us check the value once again. 1 mole at reactant side and 1 mole at the product side. So as per science, if the number of the mole of the gaseous reactant and the gaseous product are equal, then the randomness of the system from the final and the initial state will be what? Equal. So that's why we say the delta S for such cases will be taken as what? 0. Now what if I am going to substitute the value of delta H and delta S into Gibbs-Helmholtz equation? So here the delta H will be what? Negative, and if you will see, the delta S is what? 0. So in order to make this reaction, that is formation of carbon dioxide, spontaneous, or to favor this reaction, the delta G value should be what? Negative. So if the delta G value should be negative, so what should be the value of the temperature? As you can see, since the delta S value is 0, so if the 0 is multiplied with this temperature, this entire part will become 0. So even if I am increasing or decreasing the temperature, it is not going to affect this part of the equation. So here the delta G value becomes or dependent only upon delta H. It is independent onto the storm. So since this reaction is exothermic and the delta H value is what? Negative, so delta G will be negative at all temperature. So for this purpose, can we say delta G is independent of temperature? So please remember, the delta G value will not get affected for the carbon formation of carbon dioxide from the coke. So delta G is independent of temperature. In extraction process, the metal compound has converted to what? Metal. But student, we don't want metal oxide, we actually want what? Metal. So the next task is that we have to remove what oxygen, and that is the reason why this step is referred as what reduction, because the simple meaning of reduction is what removal of oxygen. Now, it totally depends upon the stability of the metal oxide, that how much easily this metal oxide can be reduced, or you can say how much easily this oxygen can be removed. For some metal which are very less reactive, this oxygen can be easily removed even by simple heating. But sometimes if the oxygen is not removed, in that cases we have to add external reducing agent. Let's say here the carbon is acting as what? External reducing agent. So carbon or any reducing agent try to break the bond between the metal and oxygen, and it tried to form a new compound or new oxide of its. So when this process proceed further, and if this metal oxide undergoes reduction, then this metal oxide will get converted to what? Metal, and this reducing agent will get oxidized to form its corresponding oxide. Now formation of oxide of reducing agent totally depends upon the rate at which this metal oxide is what reduced. I mean to say, if the metal oxide is highly stable, let's talk about this. Suppose if the metal oxide is highly stable, what it means, student? When you say metal oxide is highly stable, means what? This oxygen is strongly held with the metal. In that case, if the oxygen is strongly held with the metal, then it is very difficult to break the bond between metal and oxygen, and hence it is very difficult to remove oxygen from the metal. So metal oxide is stable in those cases where the metal is very reactive. So it totally depends upon the stability of the oxide, that how the reaction will happen. More stable is the oxide for the reactive metal, it is very difficult to reduce the metal, and that's why we say reaction will not happen. But if the reducing agent, if some suitable reducing agent is added which tries to remove this oxygen and tries to form its own oxide. So if stability of the oxide is more stable as compared to metal oxide, then this reaction will proceed. So in order to reduce the metal oxide, always we have to add such reducing agent which should able to form more stable oxide as compared to what? Corresponding metal oxide. Then only this reduction process can take place. So stability of the oxides of the reducing agent as well as the stability of the metal oxide can be decided on the basis of value of delta G. And this delta G values with respect to temperature, since it is depending upon the temperature, can be explained on the basis of one plot or one graph which we refer as what? Ellingham diagram. So Ellingham diagram is basically, if you will see, it's a graphical representation, or it is a plot between delta G value and the temperature onto the Kelvin scale. Here if you will see, onto the y-axis, all the values which are given, all the different values, they indicate the value of delta G naught. You can see it's standard Gibbs free energy, and the unit of this is what? Kilojoule per mole. So this delta G naught value is again calculated from the Gibbs-Helmholtz equation by considering all the four cases, and this delta G value is plotted against the value of temperature onto the Kelvin scale. Now the point to be noted, onto the y-axis at the origin, student, if you will see, the value does not start from 0. The lowest possible value at this graph for delta G naught is minus 1200, and as we are moving up, you can see the value goes on less negative, or you can say more value. Like the lower most value at the origin point is minus 1200 kilojoule per mole. So as we are moving up, it is becoming minus 1000, minus 800, minus 600. It is reaching to 0, and for some metal oxide formation, you can see the value is even in the positive. So overall, if you will see the y-axis, the delta G value can be negative, can be 0 and can be what? Positive. So from thermodynamics, just now we have discussed, if the delta G value comes in the negative, so the reaction should be taken as what? Spontaneous. And if it is 0, then the reaction will be at the what? Equilibrium. And if it is positive, means what? Reaction is non-spontaneous and it is non-feasible. Onto the y-axis, it will see the lowest possible value. Lowest possible value is minus 1200, and onto the x-axis, if you see, it starts from 0. It's a 0 Kelvin, you can say. And this is the temperature 0 to 500 and up to 2500. It is taken into what? Kelvin scale. So basically, this graph gives the idea of the stability of the oxides of certain elements, and also the stability is affected by the temperature. So for individual elements, if you'll see this graph where there is a formation of carbon monoxide, student, this carbon monoxide is formed from the coke. So as the temperature increases, if you read this graph, if I'm just moving towards right hand side, you can see this cursor, as if I'm moving towards right hand side, then the value of the delta G goes on decreasing. So for every step towards right, student, as the temperature increases, the value of delta G, this graph comes down, or you can say as this graph comes down, the value of delta G becomes more negative. As the value of delta G becomes more negative, what happens? The stability of the oxide increases. So this graph clearly indicates that the formation of carbon monoxide from carbon favors at low temperature, and carbon monoxide is more stable at high temperature. Of the metal oxide in pyrometallurgy or smelting process totally depends upon the stability of the metal oxides. So stability of the metal oxide can be easily explained onto the basis of what? Ellingham diagram. So stability of metal oxide as well as what? Oxides of carbon can be expressed onto this graph. This graph, which is a plot between delta G naught and temperature onto the Kelvin scale, is referred as what? Ellingham diagram. Onto the y-axis, if you will see, student, there are different values of delta G naught is given. Here delta G naught is called as Gibbs free energy, or delta G naught, you can refer it as what? Standard Gibbs free energy, and the unit of these values is kilojoule per mole. Now onto the y-axis, if you will see, there are three possible values. Some values are given as what? Negative, some values are given as what? 0, and some values are given as what? Positive. So negative value of the delta G naught indicates stability of the oxides. If more is the negative value of the delta G naught, means more stable the oxides of the element is. If you see the lowermost point onto this origin, it does not start with 0. The lowest value of the delta G naught is minus 1200, and as we are moving up, then what happens? The value of the delta G increases, it reaches towards 0, it crosses this boundary and it reaches toward plus. So all the oxides whose delta G naught value is negative, then that oxides are referred as what? Stable oxides. And formation of stable oxide where the delta G value is negative involve spontaneous process. So this clearly indicates the spontaneity of the reaction. For all the oxides whose values are in positive, or delta G naught value is positive, so that oxides are what? Unstable. And that reaction is what? Non-feasible, you can say, or non-spontaneous. Onto the x-axis, if you will see the values, which is 0, 500 to 2500 Kelvin, these all values are the values of temperature, and it is taken onto the Kelvin scale. So for different elements, if you will just check the graph, then you will find the stabilities are different at different temperature because their delta G naught values are different. For example, if you see this graph, here if you check the reaction, there is a formation of carbon monoxide and this carbon monoxide forms from carbon. So during this process, student, if you will see onto the x-axis, if we are moving towards right, then the value of the temperature increases. So as the value of the temperature increases, there is this graph falls. So this graph gives what? Negative slope. At the value of delta G naught falls, so it becomes more negative. Constantly, can you see this graph is moving? It is bending towards down. So if this graph is bending towards down, means what? It indicates more negative temperature of delta G naught. Since it indicates more negative value of delta G naught, so it indicates more stability. So every time if I am increasing the temperature for the formation of the carbon monoxide, then what happens? The delta G naught value decreases. So can I say the formation of carbon monoxide takes place at what? Higher temperature. At higher temperature, the delta G is what? Negative. So we can say carbon monoxide formation favors at what? Higher temperature. Remember, more is the negative value of delta G, more this graph will be at the lower position, more will be the negative value of delta G and more will be what? Stability. For other, if you will see, student, this graph where the carbon dioxide is formed. Now formation of carbon dioxide from the coke, if you will see, this line which is there for the delta G naught value for the formation of carbon dioxide, it is exactly parallel to the x-axis. So if this line is parallel to the x-axis, what it indicates? Even at the lower temperature and at the higher temperature or any temperature, the value of delta G naught for formation of carbon dioxide from coke remains same, remains constant. So it indicates that this process is totally independent on temperature. So formation of carbon monoxide was favored at higher temperature, but here formation of carbon dioxide from carbon is independent on temperature, because this graph is parallel to the x-axis and there is no deviation in the graph, means there is no change in the value of the delta G naught. For some metals, if you will see, or let's say the formation of carbon dioxide, earlier if you will go back, there was formation of carbon dioxide, but this carbon dioxide had formed from carbon. But in this case, student, if you will see, the carbon dioxide had formed from carbon monoxide. So formation of carbon dioxide from carbon and from carbon monoxide have different delta G naught values. So as per thermodynamics, if you will see, this reaction is what? Non-spontaneous, and it is not feasible. Why? Because as we are increasing the temperature, this graph rises up. So if this graph rises up with increase in temperature, so it clearly indicates the delta G value increases or it becomes less negative. Because at lower temperature, if you will see, it is in between minus 400 to 600. So as the temperature increases, as this graph moves up, the value becomes less negative, or you can say higher value of delta G naught. So that indicate the reaction is proceeding towards non-spontaneity. So if I am asking to select formation of carbon dioxide from carbon and from carbon dioxide, then tell me which process is more favorable. Yes, formation of carbon dioxide is independent on temperature, and formation of carbon dioxide from carbon monoxide is what? Unstable at higher temperature. Now if you look at this graph, this is the graph, if you will see, this is for the formation of the magnesium oxide. So at very low temperature, if you will see, the value of the delta G naught for the formation of the magnesium oxide is more negative. Very much negative value indicates the formation of the magnesium oxide can take place at very low temperature. Student, as you are increasing the temperature, this graph shows a sudden change and it increases. Every time if you will increase the temperature, this graph is going up. So if this graph is going up, it indicates the reaction is what? Non-spontaneous and not feasible. Means magnesium oxide is unstable at higher temperature. What it means? If the magnesium oxide is heated at very high temperature, then what happens? It can undergoes what clearly indicates that the formation of the magnesium oxide favors at low temperature. What it means? Since at low temperature the value of the delta G is very much negative, so much negative value of delta G indicates the oxides are stable at low temperature, means magnesium is ready to combine with oxygen even at what? Lower temperature. As the temperature increases, if you will see, what happens? This magnesium oxide graph of the delta G, it increases and it is going up and it is the value becoming what? More positive. So as the value becoming more positive, it indicates this formation is what? Unstable or not feasible. Above the magnesium oxide graph, you will find there is a formation of the aluminium oxide. Unlike formation of the magnesium oxide, there is no abrupt change in the graph. Like if you check the graph of the magnesium oxide, there is a sudden shift or abrupt change at this point. But in case of formation of aluminium oxide, if you will see, this graph is smoothly going up. It indicates again the aluminium is ready to form its oxide at lower temperature. This is due to the more negative value of delta G naught for aluminium oxide formation. So if any metal is ready to form its oxide at low temperature, that indicates that metal is more reactive. Above aluminium, you can find there is a formation of zinc oxide. Now zinc oxide formation, the delta G naught value is more, you can say, as compared to the formation of delta G naught value for MgO and Al2O3. So zinc is less reactive as compared to what? Magnesium and the aluminium. Similarly, if you will see, this formation of iron oxide, again the value of the delta G naught is increasing. And for the metal, if you will see, like mercury and silver, if both the graph, if you will observe carefully, for the mercury and the silver, the delta G naught value is positive. So this positive value indicates that the formation of silver oxide and the mercuric oxide is not favored. It means that silver and the mercury is not able to form its oxide at lower temperature. It means that they are less reactive metal. So if all the graph is combined together, this overall view of this Ellingham diagram will be like this. So collectively, when we discuss about the features of Ellingham diagram, so there are certain points that we can understand from this graph. The very first point, if you will see, if you will just select the formation of metal oxides. So what it says that the graph for the formation of metal oxide is a straight line with an upward slope. For example, if you see the formation of the magnesium oxide, aluminium oxide, zinc oxide, mercuric oxide and the silver oxide, as well as what? Iron oxide. All the graph, if you see, student, as we are increasing the temperature onto the x-axis, this graph is moving up. So it shows with increase in temperature, the delta G naught value for formation of the metal oxide becomes less negative or it increases. So that's why we say the graph for the formation of metal oxide is a straight line with an what? Upward slope. Let's focus to the second point. For certain points, if you will see, in formation of metal oxide for certain graph like magnesium oxide, can you see this point? Or you can see in the formation of what? Zinc oxide, and also in the formation of what? Mercuric oxide. There is abrupt or sudden change, or you can say sudden shift of this graph. So this sudden shift of the graph is obtained in formation of magnesium oxide, zinc oxide and the mercuric oxide. So what this sudden shift or abrupt change indicates? This is the indication that there is a change in the physical state above this temperature. Means if you will increase the temperature above this point where the change occur, where the shift occur of the graph, then the physical state of the oxide of the metal will change. That is the reason this graph is showing sudden immediate variations. So for which metal that we have to remember, there is a sudden shift in the graph, that is formation of magnesium oxide, zinc oxide and the mercury oxide. So it clearly indicates that there is a change in the physical state. Next point you will see, for few metals oxides like mercury and silver. Student, for mercury and silver, if you will see, the delta G naught value is at the uppermost part, and the value of the delta G naught is what? Positive. That clearly indicate these oxides are highly unstable at the higher temperature. Means if you increase the temperature, they start decomposing. So the reduction of silver oxide and mercuric oxide can be done thermally. Fourth point is that the graph for the formation of CO. Let's see this graph. If you will see, it is a straight line with negative slope. When you are saying it is a straight line with negative slope, is what? As the temperature increases, you can see this value of the delta G naught constantly decreasing. And that's why this fall in the graph totally indicates as the temperature increases, the stability of the carbon monoxide increases. So the formation of carbon monoxide favors at higher temperature. Next graph you will see the formation of carbon dioxide. Look at this graph. So carbon dioxide, if you will see, this graph is almost parallel to what? X-axis. So as this graph is parallel to x-axis and there is no deviation in the delta G naught value at any of the temperature, so we can say the value is what? Constant. So it means that even if you will decrease or increase the temperature, the delta G naught value for the formation of carbon dioxide will remain same. So can I say the formation of carbon dioxide will be what? Independent on temperature. Let's understand the significance of the Ellingham diagram. What are the advantages we are getting after learning of this graph? So some points if you will see, student, for all the metals if you will select, whether it is for the formation of the magnesium oxide, aluminium oxide, zinc oxide, mercuric oxide and the silver oxide, if you will see, as the temperature increases, the graph rises. As the graph rises, can I say the delta G value becomes higher? As the delta G becomes value higher, or you can say the delta G value for the metal oxide at higher temperature proceed towards positive value, or it becomes less negative. So the moment when the delta G naught value becomes less negative at higher temperature for all the metal oxide, it clearly indicates the stability decreases with increase in temperature. So the metal oxide which will have higher value of delta G naught or less negative value of delta G naught can be easily reduced at the higher temperature. The decrease in the stabilities is due to increase in delta G naught. You can say that delta G naught value, how it is related with the stability. Can I say higher is the delta G naught value, lower is the stability? I repeat the term. Higher is the delta G naught value of metal oxide, lower will be what? Stability. Some points if you will see, for some metal there is a deviation in the graph, and this sudden immediate deviation at certain particular temperature is observed. In case of magnesium oxide graph, formation of zinc oxide and the formation of what? Mercuric oxide. So this sudden change or sudden or abrupt change or sudden shift into the graph is because of change in the physical state. Means at this particular temperature, if you will see, there is a change in the physical state, it can be involving solid to liquid or liquid to vapor, or you can say the gaseous state. There is a graph which is having the negative slope, and this graph is what carbon monoxide formation from the coke. So as the temperature increases, if you will see, this graph falls down. As this graph falls down means there is what? Decrease in the value of delta G naught. As the delta G naught value increases, it indicates the stability of the oxide. Look at this point. More negative delta G naught or lower is the value of the delta G naught means higher stability of the oxides. So carbon monoxide is stable even at what? Higher temperature. Tendency of metal to undergo oxidation, it totally depends upon the delta G naught value. From these values, student, if you want to select which metal is more reactive or want to get oxidized faster, then you are supposed to check the delta G naught value. If the delta G naught value is what? Negative. If the delta G naught value is more negative, so that metal will be more reactive and it will form its oxide faster. So from this graph you will see the formation of oxide by metal, or you can say the metal undergoes oxidation in this order. I have taken magnesium first and the silver last because magnesium has the lowest value of the delta G naught and the silver has the highest value of the delta G naught. So lower is the value of delta G naught, higher is tendency to get oxidized. Higher tendency to form oxide means there is a higher tendency to act as a reducing agent. So if this is the tendency to undergo oxidation, then tendency or strength of the reducing agent will be reverse. Now, why this is the order followed? Because as per science or as per this diagram, it is due to the increase in the negative delta G naught value. Look here. If you'll see, delta G naught for the formation of the metal oxide increases in this order. So the lowest value is given for what? MgO, and the highest value is given for what? Silver oxide. So for lower value the oxide will be stable, and for the higher value the oxide will be not stable. For the higher stable oxide, the metal will be more reactive and it is difficult to remove oxygen, means reduction is difficult. And for higher value of delta G naught, it is easy to reduce the metal. Some importance of the Ellingham diagram. Ellingham diagram helps us to decide the reducing agent for reduction of any element oxides. In case of, if you will see, students, silver oxide and the mercuric oxide. Now let us check the position of the silver oxide and the mercuric oxide. If you will check the value of the delta G naught, then it is in positive. So delta G naught is positive for this formation. It clearly indicates silver and mercury is less reactive, means their oxidation is what? Slow process. So if their oxidation is slow process, means they do not want to combine oxygen easily, means they want to leave their oxygen easily. So silver oxide and the mercuric oxide can be reduced at low temperature even by heating without using any external reducing agent. So we can do thermal reduction for these metal oxides. So thermal reduction can be done because the delta G naught value is higher. Oxidation by these metals are slow and they will be what? Weaker reducing agent. In case of, if you will see, aluminium, if I want to reduce aluminium oxide, then generally we add magnesium. Now the question is that why magnesium is added to reduce aluminium oxide? So first we have to understand ease of formation of oxide by magnesium and ease of formation of oxide by aluminium. If I am just comparing this, then who or which metal will have higher ease to form its oxide? So it depends upon the delta G naught value. if you'll see the graph of the formation of the magnesium oxide is just below the graph of the formation of the aluminium oxide. So the graph which is below, like magnesium oxide formation, is having more negative value of delta G naught. So more negative value of delta G naught favors what? Faster oxidation process. So if oxygen is taken between aluminium and the magnesium, means magnesium will have more affinity for oxygen. So if you will take magnesium and if you will add magnesium into aluminium oxide, so since magnesium has higher ease to form its oxide, this magnesium removes oxygen from the aluminium oxide, it gets oxidized and reduce aluminium oxide to what? So in case of reduction of, if you will see this part, hematite, which is the oxide of iron, we have taken reducing agent as what? Carbon. Now if the carbon is mixed, the powder of the coke is mixed with this is also referred as carbon reduction process. This reaction is carried out about 900 Kelvin. So at 900 Kelvin, if you see into the graph somewhere here, at 900 Kelvin, what happened? At this temperature, if you see, this oxygen combines with the carbon, it forms what? Carbon monoxide, and this Fe2O3 get reduced to what? Fe. Here there is a formation of carbon dioxide takes place from carbon. So can you see this graph? If there is a formation of carbon dioxide from carbon, it is independent on temperature because there is no deviation in the graph. It is just parallel to what? X-axis. Similarly, if I am going to take zinc oxide and if I am mixing carbon, so zinc oxide, if you will see, if I am comparing zinc oxide formation and the iron oxide formation, let us compare these two graphs. Which graph you will find is at the lower part of this y-axis? Yes, zinc oxide is at the lower part of this, means zinc oxide will have more negative delta G naught value. So more negative delta G naught value of ZNO indicates ZNO is more stable. Yes, if it is ZNO is more stable, means zinc is not ready to leave its oxygen. If the zinc is not ready to leave its oxygen, then we are mixing carbon, but decomposition takes place at very higher temperature. Now the question is that why reduction of iron oxide takes place at lower temperature and the reduction of zinc oxide takes place at higher temperature? The reason it is because of the difference of stability of Fe2O3 and ZNO. ZNO, if you will see, since it is occupying at the lower part of the y-axis, it indicates it is having lower value or more negative value. So more negative value means what? Higher stability. So in order to break higher stable metal oxide, reducing agent is mixed and it is heated at very high temperature. So reduction takes place at different temperature with the formation of C. Here there is a formation of carbon dioxide from carbon, which is independent on temperature. And if you will see, there is a formation of carbon monoxide from carbon. Can you see this graph? Yes, this graph with the negative slope means if the temperature increases, the stability of the carbon monoxide what increases, means zinc oxide can be reduced to zinc at very high temperature. Look at this. But this graph is what? Parallel to what? X-axis. It shows there is no deviation. So it is independent on temperature. You got this? Around 1000 unit, if you will see, there is a point of intersection where the value of delta G naught of formation of CO from C and the CO2 from C becomes equal. So if I am comparing this, all the three graphs, can you see this brown line? This brown line is indicating formation of CO2 from C. So it is totally dependent upon what? It is totally independent upon temperature. As there is no deviation, there is no fluctuation into this graph. So let us try this graph of formation of carbon monoxide, this pink one, from the carbon and the formation of carbon dioxide from the carbon monoxide. So if you will see, this formation of carbon monoxide, I'm talking about the peak graph, it falls down, it is with the negative slope, and this graph which is just going up gives what? Positive slope. So carbon monoxide can be better reducing agent as compared to this, because carbon monoxide, the value of delta G naught is what? Increasing. So as the delta G naught value increases means what? Formation of carbon monoxide at higher temperature is what? Now if you will compare this, all these three graphs which are indicated with the different colors to understand. So this graph, this brown line which indicate formation of carbon dioxide from carbon, this graph, since it is parallel to the x-axis of the temperature, so there is no deviation, there is no fluctuation into the graph, so it shows that it is totally independent on the temperature. So if you are neglecting this formation of CO2 from C, student, if you will see, there is a formation of this pink line. So this graph, the value of the delta G naught continuously decreases with increase in temperature. It indicates the stability of carbon monoxide. Carbon monoxide is more stable if it is prepared from carbon at very higher temperature. So carbon monoxide stabilizes at higher temperature. And in this black color line, if you will see, where there is a formation of carbon dioxide from carbon monoxide. So this shows what? Positive slope, which indicate the delta G naught value is what? Higher. So if I am comparing both the cases, so tell me the ease of formation of carbon monoxide and ease of formation of carbon dioxide, which is more? So for that purpose, we have to check the delta G naught value. So delta G naught value for CO is more negative. So ease of formation of CO is faster as compared to what? CO to form CO2. That's why we say at lower temperature, if you compare at lower temperature. So lower temperature means before this point of intersection, this black line is what? Occupying the lower portion of the delta G naught. It indicates at lower temperature, if I have to select what? Reducing agent. So reducing agent can be what? CO. So that's why we say CO is the better reducing agent, because at lower temperature before this point of intersection, it is having more negative value of delta G naught. So let us understand some application of Ellingham diagram in order to decide the reducing agent at certain specific temperatures. Suppose if they will ask a question like this, can carbon reduce ZnO to Zn, and they have given two different temperatures. The first temperature which is given is what? 1000 Kelvin, and the second is given 1500 Kelvin. So to answer this, we have to first check the formation of ZnO as well as the oxide of carbon at both the temperatures. Generally, if the carbon, that is the powdered form of the coke, is mixed with the oxide of the zinc, then this reaction takes place like this. If there is a reduction of zinc oxide takes place, it gets converted towards zinc and there is a formation of carbon monoxide. So we have to check the value of formation of ZnO as well as formation of CO from C at 1000 Kelvin into the graph. Student, if you check this graph, then this delta G naught value is plotted and this is for temperature. So they have mentioned at 1000 Kelvin. So at 1000 Kelvin, if you check the formation of CO from C, then the value of delta G naught at 1000 Kelvin for formation of CO is minus 400 kilojoule per mole. And let's say this is the plot of formation of ZnO. Then for ZnO, if you will check the value, so at 1000 Kelvin, the value of delta G naught for the formation of ZnO is around between minus 600 to minus 400. Let's say if it is minus 550. So from this graph, we got the value of formation of CO from C and formation of ZnO at 1000 Kelvin. So the values can be written it like this. Now if you will add these values, student, then what is the final answer you will get? If you will add it, you will get 150. Irrespective of the values, can you please check this sign? It comes in what? Positive. So it comes in positive. It means the reaction is not feasible. So this reduction cannot be carried out at 1000 Kelvin. But if you will check at 1500 Kelvin, student, then the formation of CO delta G naught value and the formation of ZnO, it is 1500 Kelvin. The value is not same as it was there in the 1000 Kelvin. Now this time the value is minus 500. And for formation of zinc oxide, if you will see at 1500 Kelvin, if you will check the value, this value is at between minus 400 to minus 200, and it is somewhat minus 250. So the value which we got for this delta G naught from the Ellingham diagram, if we'll add it, irrespective of the value, if you'll check this sign, it is what? Negative. So if the delta G is negative, so as per thermodynamics, the reaction should be what? Spontaneous, and it should be what? Favorable. So if we want to carry out the reduction of ZnO by using carbon, the temperature should be what? 1500 Kelvin. It will not reduce below 1500 Kelvin or 1000 Kelvin. Got this? You can say some conclusion about this Ellingham diagram. There are certain limitations also associated with this. For example, some points like Ellingham diagram tells us about at which temperature reduction is feasible for the given combination. Can I say lower is the position of delta G naught value of the element, more negative will be its delta G value. You have to check the graph. If the graph is occupying lower position onto the y-axis, means it indicates more negative value of what? Delta G. So it means that it can reduce all the metal oxide above it, correct? For example, if I am taking magnesium, see, magnesium is occupying the lowermost position onto the y-axis. So can I say the magnesium oxide formation will have the delta G naught value? So can I say magnesium have higher E's to get oxidized? So if the magnesium has higher E's to get oxidized, means magnesium can reduce other metal oxides easily. Along with this, there are certain limitations also associated. Ellingham diagram tells only about whether the reaction is feasible or not, but it cannot tell about kinetics of the reaction. There is no information available for the kinetics of the reaction. We cannot say how much faster or how much slower the reaction can be take place, or it can be explained. Since delta G naught value is associated with the minus RAT ln K, where K is called as what? Equilibrium constant. Thus, it presumes that the reactant and products are in what? Equilibrium. But it's not true about all reactions. Well, so before proceed further, let us solve this worksheet on the basis of Ellingham diagram that we have done. Let us see the very first question involves match the followings, and the second is what? True and false. So all of you can pause the video, go through with the questions and find the correct answers, and after 2 to 3 minutes I will discuss the answers. Come on, time starts now. So let's check the answers. The very first question is what? Match the followings. In column 1 they have given the properties that is taken from the Ellingham diagram, and in the second against it they have mentioned some property. So we have to find the correct answer for the appropriate reactions. If you will see the first one, which says that values of free energy, here the free energy is what? It is delta G. More correct to say delta G naught, which is referred as what? Standard Gibbs free energy. So delta G naught, which is plotted onto the y-axis versus temperature onto the x-axis. So values of free energy show sudden change. In what cases there is a abrupt change or shift, or you can say jump into the values of delta G naught. So that metal should be, there is a formation of oxide of magnesium oxide, zinc oxide and mercury oxide. If you check the graph of formation of magnesium oxide, zinc oxide and the mercury oxide, there is abrupt or sudden shift in case of their graph of the delta G naught values. Second, they have asked is what values of free energy remains unaffected with change in the temperature. For which reaction the formation of oxide does not depend upon the temperature. So that reaction is what? Formation of carbon dioxide from carbon. In this case, if you see, the graph remains parallel to what x-axis. There is no deviation in the graph. So there is no deviation in the graph. It clearly indicates the values of delta G naught does not change with respect to what temperature. Values of free energy shows a negative slope with temperature. This is for the formation of carbon monoxide from carbon. For this graph, you will see every time if the values of temperature are increased, then the graph falls down, which shows that stability of the carbon monoxide at higher temperature due to the lower or more negative value of delta G naught. Oxides which can be thermally reduced. So the graph should be onto the upper part onto the y-axis, and these oxides are silver oxides and mercury oxide. Now, what is the reason why they can thermally reduce? The reason is that they have higher, or you can say positive value of delta G naught, which says that the oxidation is what slow process, and these oxides are unstable at higher temperature. Let's move to the true and false cases. The very first statement they have given that positive slope of lines indicate stability of metal oxide decreases due to increase in the values of the free energy. The statement is true because the statement is based upon one relation where more is the negative value or more is less value of free energy, higher will be the stability. So when you are talking about positive slope, so it indicates decrease in the stability of the metal oxide. As the value of free energy increases, the stability decreases. The first statement is not true. Second one, if you'll see, negative slope. In this case, the graph falls down. In negative slope, the carbon monoxide indicate it becomes more stable with increase in temperature. Yes, student. Again, the same principle is applied. Lower is the value of delta G naught, higher is the stability. So the statement is what? True. Third, if you'll see, in case of silver and mercury, the graph are at the upper part in the Ellingham diagram, indicating more tendency to form oxide. No, the statement is false. More is the upper position of the graph onto the y-axis. That shows that oxidation of that element is difficult. So their ease of oxidation decreases. So their oxide are unstable at higher temperature. Fourth, if you see, the order of formation of oxidation follows this order. It is false because the order should be reversed. Why I am saying the order should be reversed? Because if you check for the magnesium, the delta G naught value of magnesium is at the lower part of at the y-axis. So more lower position of the graph onto the y-axis. So more negative or less value of delta G naught, which indicates higher stability. So here the magnesium should oxidize first and silver should oxidize last. So the order should be what? Reverse. That's why the statement is what? False. Fifth, if you will see, an element can reduce the oxide of another element below it in diagram. No, it is false. The element can reduce oxide of the element which is above it. So that need to be changed into the statement. 6, if you will see, the more negative values of free energy indicates higher stability of oxide. Yes, this statement is what? True statement. Got this? Let's solve another worksheet on the basis of Ellingham diagram. The questions which are related here is we have to find appropriate scientific words. So let us try to solve all these questions based upon the fill in the blanks, and you can pause the video and after 3 to 4 minutes I will give you the answer. So please start solving. Please do not copy the question, student. You just write the correct answers. Come on, start now. Okay, let's check the answer. The very first, if you'll see, they have asked formation of metal oxide is dash process and it is always dash. So formation of metal oxide is a type of combustion process, and all combustion process as per thermodynamics is what? Exothermic. Second, formation of metal oxide favors at dash temperature. It is at low temperature. Third, if you will see, formation of carbon monoxide from carbon favors at dash temperature. It is favors at what? Higher temperature. Fourth, formation of carbon dioxide from carbon gives free energy values are dash on temperature. Since there is no change in the temperature, so we will say it is independent on temperature. Independent on temperature. Okay. Graphical representation of values of free energy and temperature can be explained by Ellingham diagram. 6, if you will see, more negative values of free energy of formation of metal oxides indicate the process is, as per thermodynamics, the process is spontaneous, or you can say feasible, and oxides are stable. They are stable oxides. Formation of metal oxide which shows sudden change. If there is abrupt change or shift, so these oxides are formation of magnesium oxide, zinc oxide and mercury oxide. 8th, if you will see, ease of oxidation by different metals are. Ease of oxidation depends upon the values of delta G naught. So we have to select a metal which will have the lower value of delta G naught. So this order, if you see the graph, the lowest position of the graph onto the y-axis is what? Magnesium. Above it there is what? Aluminium. Then it will be chromium, then iron, and the last you can see it is what? Silver. So it is the ease of oxidation. And 9th, they have asked order of reducing strength. See, reducing strength depends upon the ease of oxidation. So higher or faster is the ease of oxidation, stronger will be the reducing agent. So the answer will be the C, magnesium. It will be aluminium. Then it is chromium, iron and silver. The metal which will get oxidized faster will act as stronger reducing agent. 10th, it will see, Ellingham diagram enables to select a suitable reducing agent for a dash of metal. Here the word should be what? Reduction of metal oxide. An element can reduce other oxide element. It should be above it in the diagram. So these are the simple questions that can be asked on the basis of Ellingham diagram. I hope you understood this.